last day. I finished from here, from these two propositions. Okay, let's check this example. So we have observations from that X column. There are 6 observations. So we are going to find the variance. Okay, S squared. To do that, we need X minus X bar. First of all, we need to find what is the mean of the what is the sample mean X bar. So first you can find the X bar, then you can fill the second column, X minus X bar, which means you have to subtract X bar, which means sample mean, from each observation. Okay, see, 1,600 minus 983.5, so that you can get 616.5. Okay, something like that. Fill that column, then square that column, which means third column. Okay. Now you have what you need. So from top to bottom, get the sum. So total sum going to be this one. Then plug the values to that equation. S squared equal summation of xi minus x bar square divided by n minus 1. N is here, n is 6, so n minus 1 is 5. So you can get the variance. Okay. Once you need to find this standard deviation, take the square root of S squared. Okay. Okay. So standard deviation is 347.2. Okay. 5-number summary. We have already done this 5-number summary. Minimum, Q1, Q2, Q3, and maximum. It is a quick summary of both center and spread. Okay. So, okay, next plot is box plot. We have done histogram, stem leaf plots, the bar chart, these kind of thing. Then there is one thing we need to do: box plot. Box plot is some kind of special case. I mean, special graph, because box plot shows 5-number summary. Okay, minimum, Q1, Q2, Q3, and maximum. Okay, those are the only thing we have mentioned in the box plot, except outliers. Okay, 5-number summary and outliers we mention or we show in this box plots. Okay, you will see that it's a graphical representation of 5-number summary. It is something like this. First, I mean, the left end is the minimum, then Q1, Q2 or your median, then Q3, and finally maximum. Finally maximum. Okay, 5-number summary. Right now I'm not going to consider outliers. We will consider that later. Okay, so this is the shape of the box plot. Though this axis, I mean the scale, the horizontal line, gap between minimum and Q1 or any other gaps that can be changed due to the scale. Let's say I think we have example here. So this is the outlook of box plot. Okay, you can draw it either horizontal or vertical. That's not a problem, but scale should be there, and you have to mention what are these minimum, minimum, Q1, Q2, Q3, and maximum. That's very important. Okay. Okay. Okay, you have these observations. There are 3, 6, 9, 13, right? 3, 6, 9, 10. Yeah, 13 observations. Okay, so first sort them into ascending order. Then you can find what is the minimum, what's the maximum, Q1, Q2, and Q3. Okay, so you can see here minimum is -12. Okay, so This is the median 1.4 because you have an odd number of observations. So n plus 1 divided by 2 is the, I think, sixth position. So simply you can take the median, then get the first half and the second half, find the Q1 and Q3. Okay. Okay. Now you have these 5 numbers. Minimum -12, Q1 -1.5, Q2 or median 1.4, Q3 3.7, and maximum 7. Okay. So now I'm going to plot this. These are the values. Here I have mentioned no outliers. I'm not right now. I'm not going to consider outliers. Okay, just forget about it for a moment. Okay, this is my scale. I'm going to draw the box plot. So this is the box which mentioned Q1, Q2, Q3. Okay, order should be there. First Q1, Q2, Q3. Okay, then minimum. Right hand side maximum. Okay, normally we end them like using these vertical lines from the beginning and at the end. Okay, so you can see here gap between minimum and Q1, it is larger than the other gaps, right? Why? Because those values, gap between -12 and -1.5 is much larger than other gaps. Okay, clear? So I don't need to draw this like perfect scale, but try to draw it like try to draw it like something makes sense. Okay, clear? Normally that's how we draw this by hand. Scales can be changed, but when you use a software, it gives you a perfect box plot. Okay, so keep this in your mind. Please keep these correct gaps between those values. Okay, you don't need to color this. That's fine. Inside the box, gap is there. Okay, so middle line in this one. Where is okay? This line. Oh, so this can be shift left side or right side according to those values. Okay, that can be happen. Something like let me draw another example like this. Okay, let me draw this one. Like, this is the box, minimum, maximum, and this see, this is the mean. This is the max. This is Q1. This is X tilde or median or Q2, whatever. Okay, and this is Q3. See, gap can be like this or this in your picture. Okay, clear? Okay, here I have mentioned 2 box plots. You can see the scales. Okay, they have same median, but they have different Q2, Q1, Q2, and minimum maximum. Okay, so these are the values. Okay, clear? Okay. There is one more thing we call fourth spread, but I'm not calling that fourth spread. We called it interquartile range. If you remember, I told you in the chapter 1.2, we have something that we can deal with outliers. This guy, interquartile range. Interquartile range mean Q3 minus Q1. Okay, range between third quartile and first quartile. Just a number, just a value. Okay, Q3. This is the quartile one. Sorry, this is the third quartile. This is first one. So Q3 minus Q1 is the interquartile range. I call this interquartile range, or you can call it fourth spread. Okay, so if we have an outlier or many outliers we can track using this interquartile range. To do that, we do very simple calculation like plus or minus 1.5 times or 3/2 times this fs, plus or minus 1.5 times fs. Okay, so uh, okay, let me draw our box plot. uh, okay, this is my box plot. This value is minimum. Right now this is minimum, this is maximum. So we have q1 here, q2, I'll mention it q2, okay, and q3. Okay, so always we find outliers from left hand side now, right hand side. That's the definition of the outlier. Okay, outliers can be far away from the its center. Okay, first we need to find is there any outliers from our left hand side or from the beginning. So what we have to do is pick q1 and do this calculation. Left hand side, q1 minus 1.5 times fs. Fs is interquartile range, q3 minus q1. Okay, so that I don't know where, but definitely this value, this this value less than q1, right? It is subtract something from q1. So q1 is here, this calculated value somewhere here. Okay, so we can consider start from there, then right hand side maximum part. So for that case we add 1.5 fs to q3, so that value greater than q3. See, so that you have to consider your range something like this. It can be inside the minimum and maximum or outside the minimum and maximum. That's okay. This is just an example. Okay, so this brackets shows you how we what is the area or what is the range that we are considering. Okay, so whatever outside this brackets from the left hand side to right hand side, whatever outside this bracket we call outliers. Clear? If anything outside this bracket we call outliers, and we denote that outliers by using star marks. Okay, star marks on top of this axis. Or if let's say here we don't have our axis, but this we call an outlier. It can be one outlier or many. That's fine. Okay, we can extend this outlier measurement to like some extent, like expanding this 1.5 to 3.0. I mean double the size, not double but double the value. So in that case we call that extreme outliers. First we found just outliers, now we are going to find extreme outliers, go beyond that. To do that same way, but the values this q1 minus 3 times fs, and also from the right hand side q3 plus 3 times fs. Okay, so that the range can be little bit bigger than the outliers. Okay, so whatever outside in that range we call, from the left hand side or right hand side we call outliers, and we denote them by star marks. Okay, okay, here I have mentioned q1, q2, q3, and an interquartile range as well. So let's find, do we have outliers or not? First, consider, that's my, okay. First, consider Q1 minus 1.5 times Fs or IQR. This is your Fs, okay. So this calculation, you can see Q1 is 35 minus 1.5 times 17 is 9.5, and Q3 plus 1.5 times Fs is 77.5. Now you can see from left hand side, 9.5 is somewhere here and 77.5 is somewhere here, right? So we have outliers, right? We have from the left hand side, we have 7, which is outside the boundary, and from the left hand, from the right hand side, we have 105, which is also outside the boundary. Clear? Okay, I use the same example to I use same example to explain minimum and maximum as well. Once you consider everything, I mean, in the first place, I need to find the minimum and maximum. Okay. Without considering these calculations, what is the minimum and maximum? 7 and 105, right? But once you figure it out, what are the outliers, then you have to change your minimum and maximum. Okay. So now this is the boundary. So whatever you have to consider, whatever you have to consider within this range. Okay. So now your new minimum and maximum is 32 and 72 respectively. Okay. Clear? So you have to change that according to the outliers. After you figure it out what are the outliers, definitely you have to change it, your minimum and maximum. Okay. I think it is, yeah, I mentioned there. So new minimum and maximum is 32 and 72. Okay. If you don't have any outliers, then that's fine. Otherwise, you have to change accordingly. See, these are the outliers mentioned by a star mark. Yes.
So are like mean, median, and change either? Or still like including those calculations?
This is only for box plot. This outliers we are considering only to draw the box plot. Okay. So once you have to consider the minimum, mean and median, then in the question they will mention that you have to consider after this or before that. Okay. But once you draw the box plot, always try to first find the outliers. If you have any, then mention it and draw the box plot. Okay. So always outliers deals with this box plot. Okay. Yes, sir.
Please explain one more time why 32 and 72 are the minimum and maximum, not 7 and 105.
Yeah, sure. In the first place, when you check our original observations, minimum and maximum is 7 and 105. Once you find the outliers, if there is any outliers, like here see, our boundary value is 9.5 and 77.5, which means that's the maximum width or maximum range that we can approach. Okay. So 9.5 is somewhere here, right? And 77.5 somewhere here. Since we are considering that range, we cannot go further. Whatever outside that range, we consider outliers. So we have to remove outliers. So yes.
So Q1 and Q3 are the range for it to.
They don't change.
Yeah,
Q1,
yeah.
Q2, Q3, they don't change.
The range for it to find out the outlier. That's it.
Sorry?
Make it the range for it to find the outlier.
Yes.
Okay.
Yes, exactly. Right. So we just remove our outliers, and find what are the new minimum and maximum. Those minimum and maximums are 32 and 72. Clear? So you have to mention that if there is any problem like this with outliers, yes, you have to mention. Not simply first one and last one. Check whether there are any outliers, then check what is the minimum and maximum. Okay? And also, don't forget to mention outliers by using this star marks. Okay? Here they have like draw this separate case, but don't separate it. Just it's like just a one box. Okay? Don't separate it. Either you can mention min Q1, Q2, Q3 max, and you can mention what are those values, or simply mention values like this. That's fine. Okay, but definitely mention what are the values. Okay, otherwise who knows what are the values? Clear? S1 and S, they are like they give better performance if we have a symmetric or approximately symmetric distribution. But if we have like
Hello.
skewed distribution, we those results S1 S squared and S results they can be like biased because of the outliers. S, I have mentioned here, SOS squared should only be used with X bar. Why? Because we use X bar to calculate the S and S squared, right? We don't use median. Okay, that's why we just stick with that X bar. Once you use S squared, variance or standard deviation, should only be used with X bar. Okay, not the median. Phi number summary is the best used of skewed distribution. Yeah, why? Because it considers only locations rather than values. Okay. Or those having extreme outliers. Okay, that's the end of that chapter. Any question? I'm going to start the chapter 2, sample space and events. Okay. First, consider an experiment. Experiment, it is something we call an environment. We can do our activities or process whose outcomes are uncertain. But the thing is, in this experiment, in all experiments, we know what are the outcomes all the outcomes that we can get. We already know before the experiment what are the outcomes, all the outcomes that we can get. But the problem is we don't know what is the exactly what is the outcome which we can get at a certain time. Clear? Like flipping a coin. We know a coin has only two sides, head and tail. When we flip, we don't know which side we appear in the surface. Okay, it can be head, tail, something like that. So flipping a coin we call an experiment. Clear? Rolling a die, tossing a coin, picking a card from a deck. So there are so many. Okay. Sample space. So sample space mean all possible outcomes that we can get from that experiment. All possible outcomes. Okay. Set of all possible outcomes. These are normally we denote by sets. You know sets, right? That's how we denote these sample space. Normally we denote it by capital S. So when you read some books, you will see sometimes we use omega, capital omega, capital omega to denote the sample space, this symbol, or you can use capital S, whatever. Okay. Some books they have mentioned capital omega to denote the sample space. Okay. So examples, I think I have mentioned example in this slide. Okay, these are the examples with well numbers. Uh, Tossing a balanced coin. Why I mentioned balanced? Because sometimes we have unbalanced coin as well, or we call biased coin. The thing is, if it is a balanced coin, which means it has equal chances to get head or tail, like 50-50. But sometimes some coins they are biased, like head can appear like 70%, so tail can appear only 30%, something like that. It's possible. Okay. And there is another coin we call, it's theoretical one, fractional coin flipping we call that, but it is just theoretical one. Okay, we cannot flip it. So if we are considering a balanced coin, then we have only head and tail. Those are the all possible outcomes, head and tail. Since we mentioned by using sets, we denote it by like this within curly brackets and separate them by a comma. Okay. Or you can write it head and tail, or you can write it H and T, H comma T, head or tail. Okay. Let's check third one, rolling two dice. Rolling two dice. Same time you roll two dice, so that you will be having 36 outcomes. Why 36? Because one die it has 6 sides, the other as well. So first die appears 1, but second die appears 6. So the pair, that outcome is 1 and 6. So likewise, you will be having 36 outcomes. If you have a pair inside the sample space, you can mention it by brackets, just brackets. Okay, so you separate it. Okay. Okay. The next important thing is an event. Event is very easy. Event is a subset of sample space, like this. No need to go too much theories. Just try to keep this in your mind using these simple cases. So this is my sample space, and I'm getting this portion from the sample space, and I call this an event. Okay, it's a subset of sample space, which means I'm considering heads only. It's a subset of head and tail, the first example. Okay, something like that. You will see more examples later in later slides. Event is the simplest case. You can consider just one outcome, or you can consider event including many outcomes. Okay. Compound, we call that compound. Compound if it consists of more than one outcome. Okay. Event can be like simple or compound. This example, I don't think you can get many things, but in this example, they are talking about 3 vehicles, freeway exit turns left or right. So 3 vehicles, these are the outcomes, all possible outcomes, right? LLL, RRR, right? Those are the outcomes. So this is an event, E1. See, all 3 vehicles turn left, or all 3 vehicles, E8, all 3 vehicles turn right. This we call a simple event. Okay. But if we need a compound event like this, capital A, this one, right, one vehicle turn right, others turn left, something like that. Okay, which means simply exactly one vehicle turn right, others turn left. So event you can mention by just writing it, write it like this. The first one, A equals that part equals the event that exactly one of the three vehicles turn right. Okay, like that you can mention it, or you can denote it by like that by using letters. And also I forgot to mention events we denote by capital letters. Don't denote it by simple letters. That's a normal procedure. Capital letters. Capital A equals this event. Capital C equals this event. Something like that. Okay. Okay. Why this is not going? Oh, sorry. This is not going until I check the chat. Okay. Rolling two dice. Then I have mentioned what is my event. You know what are the outcomes between S for rolling a die, rolling two dice. Sorry, rolling two dice. So you know what is S, right? All possible outcomes. I have mentioned what is my event. A is having sum of the two dice less than or equal 5. So their summations should be less than or equal 5. Okay, so these are the possible outcomes for that particular event. Same way, A equals, sorry, A equals within square bracket, mention the pairs, all possible outcomes. Okay. Event B, yes. So you can define any number of events for particular experiment. There are a few relations. We call this set theory because we are dealing with sets. Um, complement. Complement of an event, which means uh, everything except that event. Okay, everything except that event. So we denote complement by writing like, let's say we have an event A, capital A. So complement is just like a comma on top of that letter. Or some books they mention, those writers they have mentioned complement like C, complement C, A, C on top of that. That's fine. Okay, so you can use whatever you want. Clear? Okay, and the next one is union. Union mean uh, consist of all outcomes in that events, in those events, not that event. Consist of all possible outcomes in those particular events, right? Whatever, in this case you have A and B, so union of A and B mean all outcomes that uh, include to A and B, all outcomes. Okay, so I'll show this using Venn diagram later. uh, so all outcomes that are either in A or B or both events. Okay, everything. uh, Next one is, so where is my cursor? Okay, intersection. Next one is intersection, which mean only the common space. They share the shared space. So we have to consider only the shared space that belongs to A and B. Okay, only the shared space consists of all outcomes that are in both A and B. Okay, so union we denote by something like letter U. It's not letter U, it's a symbol. Okay, so you can see here. See. Or you can simply write it A O B. A O B by letters. Intersection you can denote by like this. It's again a symbol. Or you can write it A and B. So intersection, that keyword is and. For the union, keyword is O. OR. Okay. Oh, sorry. I think, yeah. Let me check. Yes. So using Venn diagram, I can show you if my event is this one, oh sorry, this one, then what is A complement? Complement of A, which means A dash is this space, right? So could just consider everything within this box. A complement, yes, mentioned here. It doesn't matter how many events that you have. So union is this, the last one, union, and intersection is the third one. Okay, command space only. Clear? So it is very easy to show by using Venn diagrams. We can extend this like 3, 4, 5, 6 many events, but Venn diagrams, it has its own limitations. So when we increase the shapes like circles, triangles, whatever, it's hard to get an idea. Okay, so we can mention 3, 4 events using Venn diagrams, right? But you can extend it without any problem. Okay, I think this is okay. Null event. I didn't tell you. We have sometime. I mean, always if there is no event, there is a one event we call null event, which means nothing is there. It's just empty. Sometimes we call empty set, same name, but we denote this null set using this notation. I don't think you need that, but we use null set using this notation, which means nothing is there, just 0 and cross it. Okay, uh, that's we call null event. There is no outcomes. So every event or every sample space, they had every sample space, it has a null set, or we call a null event. Okay, but we don't need to deal with that. If there is if question ask, okay, but mention the null set or whatever, we don't need to mention that, because we just forget about it. Okay, it's there, but sometimes we don't care about it. Okay, I think, yeah, there is a law we call commutative law, which means we can interchange our events. Like if we have event A and B in this like this example here, we have like this. We have something like this left hand side, A and B. A intersect B, or A and B. Then we can change it like B and A. Okay, it doesn't matter how many events you can do the same. Commutative law, you can interchange those events. Okay, example is there. Let's consider this example. Consider rolling 6-side die. Okay, I think yes, A is the die shows up an even number, B odd numbers, C prime numbers. So this is the sample space for one die, just one. So A is the even numbers, odd numbers, prime numbers, right? So you have to mention it like set. Okay. So what is A dash? Everything except A. Okay, except A. Same here. A union B, which means even numbers and odd numbers. So this one. Okay, clear? So I'm not going to one by one. Do we have intersection for A and B? No, there is no common elements in A and B, because odd numbers and even numbers. So it is empty. Or you can mention it like null set. Same thing like this. But it is better you can stick with this notation what we have mentioned in this slides. Okay, but some books, yes, still we use that notation. Okay. Okay, this is very important. Okay, let me think an example for mutual exclusive. Okay, mutually exclusive events mean they are totally disjoint. I mean, they are separate cases, it's like you and me. We are totally, I mean, separate cases. You studying, you do your undergrad this stuff. I'm separate on, I'm studying, I'm doing something like that. Okay, separate cases. We don't have common things. Something in common we don't have. Okay, which means intersection between those two events are zero. There is no intersection between those two events. Clear? So two or more, it can be two or more events are mutually exclusive if no two of them have outcomes in common. Okay, that's we call mutually exclusive, which means, let's say we have event A and B. A intersect B is null. Okay, simply we call zero. There is nothing in common. Okay. Example, a rolling die example, event A dies. Yeah. In previous case, A and B, this one, see, these are mutually exclusive events, A and B, right? Okay. Yes. Two very important laws we should know when we are dealing with sets. Those we call De Morgan laws. Those are really important, because sometime if you have to prove something, prove this kind of stuff, not this kind of, prove something, definitely you can plug this De Morgan laws and get the results. Okay, these are very important. I'll show first one, then you can try the second one. These two we call De Morgan laws. Its first one says A union B dash, which means A union B complement equals to A complement and B complement. Okay. Okay. Let's check the first one. I mean, left hand side. I'm considering this one only. Okay. Oh, sorry. Here it is dash. Let me draw it again. I'm considering this one only. So let's do this by using a Venn diagram. Okay, this is my S, capital S sample space. So I have two events, A and B. This is my B, and this is my it's gonna be a problem. Okay, this is my A. So first one says A union B. Let's say okay, A union B. Just consider A union B, this one, right? A union B is this one, but it says A union B complement, which means this area. Okay, this area, the blue color area. Okay. Okay, let's go to the right hand side now. It says A, B, this is my B, this is my A, and this is my sample space. So it says A complement and B complement. So first A complement. A complement mean this area, right? Right? Including this. Okay, A complement. And what is the B complement? B complement mean whatever except this area. I'll use another color. Sorry for my drawing. Those are not Beautiful. So B complement. This is the B complement. So it says intersection and. So what is and? So what is the area that colored using red and blue both? Outside, right? Whatever outside this part. See? Okay. So they are same, right? So simply by using a Venn diagram, you can prove this De Morgan law. And also by doing some proofs without drawing this Venn diagram, you should be able to prove that as well, right? I don't think we have that, but oh, I'm so sorry. It is, oh no, we have 1 minute. I don't know this. So anyway, but I don't think you have to do it. I didn't see in homeworks, but we should be able to do that by using complement, take inside and everything change, but no problem. You don't need to think about that. We can prove De Morgan laws by using Venn diagram. Please go home and try the next one, second one. Okay, same thing, same concept, just play with these symbols, play with these graphs. Okay.